Hi, today's video I'm going to go over the Wittig reaction, which is a very useful reaction for forming an alkene, and then also it brings together two compounds into one. So those are the two big positives of this reaction. So the Wittig reaction uses a reagent called an aldehyde. Weird spelling. Also, it's a kind of weird looking reagent. It's called an aldehyde because you have a negative formal charge adjacent to a positive formal charge. Now you'll say, yes, there's resonance here. Okay, I can draw a resonance structure and I would get this. You can do that. A couple notes, phosphorus can make 5 bonds because it's not one of the second row elements, so it has extra orbitals to allow for the formation of 5th bond. So that's okay. The reason that the structure over here is actually more favored, which is different than usual resonance structures, because generally you don't want to have formal charges if possible. Right, carbon and phosphorus are very different sizes. Phosphorus is a bigger atom. Because of that, the p orbitals of phosphorus are larger than those of carbon, so there's not very good overlap between the phosphorus and the carbon p orbitals. So if there's not good overlap, you're going to have trouble forming that double bond. Right? So that's the reasoning you have the negative and the positive formal charge next to each other. So what happens in a reaction, in the Wittig reaction specifically, is if I start with a ketone or an aldehyde, in this case I'll use a ketone, if I were to react it with what I have above here, I would get the following. That would be my product. Right, numbering the carbons, 1, 2, 3, 4, 5, 6. I would have 1, 2, 3, 4, 6, 5. Those would be the carbons. All right, so now I'll go through the mechanism of the Wittig reaction. So step 1 is going to be the formation of aldehyde. So I start with this phosphorus with 3 phenyl groups on it and a lone pair. It will react in an SN2 mechanism. Kick off the iodide, so I'll get that. And this would actually be, I'd have this group, right? So next thing I'm going to do is react with a very strong base, N-butyl lithium, which is just butane that's been deprotonated. Right, so this will come and deprotonate one of the hydrogens, and then that gives you your aldehyde, because now you have the lone pair on the carbon there, and then you have the positive formal charge on the phosphorus. So there's my aldehyde. So next, the aldehyde is going to react with the ketone or the aldehyde. So I'm going to choose that to be my ketone. And I'm going to use different colors here to help with showing the reaction. and then I have my ylide here. I have the 3 phenyl groups. So positive formal charge, and then the negative charge. This is going to be a 2 + 2 cycloaddition in the first step. So one of the pairs of electrons from the double bond here will go to the phosphorus, and the lone pair from the carbon will come and attack the carbonyl carbon. So now I will have the following. Notice all of the formal charges have gone away because I have 5 bonds to the phosphorus now. So formal charge of 5 minus 5 there is 0. And the carbon, I no longer have a lone pair. I have 4 bonds to it. Now, the reaction I'm going to get here is the bond between the carbon and the oxygen right here. These electrons will move over to form a double bond there. And then the electrons between the phosphorus and carbon will move to form a double bond between 2 carbons. So now, my final product, I'm going to get this, but that's just, a product that we're not concerned about, plus the alkene that I was looking for. And I get my final alkene product. Again, numbering the carbons, 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. So on here, this would be 1, 2, 3, 4, 5, and 6. So it's important with a reaction like this to make sure you are numbering at the end or during it to ensure you have the correct number of carbons on your final product, and also that the carbons that should be bonded to each other are bonded to each other. Now a couple more notes. Since the ylide is prepared via an SN2 mechanism, we need to follow the SN2 rules. Right? So you can't have, when I'm preparing this, right, I can't react this with a tertiary iodide because I can't undergo SN2. Right, so that's something to remember. I can't undergo SN2 with a tertiary substituted iodide, so this won't happen. And I'm using iodides here. You could use any alkyl halides, so chloride, bromides would work as well. One other note is you'll sometimes have options with what compound will be your ylide and what will be your ketone or aldehyde. So say I'm trying to form this as my product. I have 2 options. Right? Option 1, I use an aldehyde, and then my ylide, which I'm going to write in its abbreviated form, would be this compound here. This would be carbon 1, 2, 3, 4, 5. Over here, this would be 1, 2, 3, 4, 5. My second option is going to be a ketone, and then my ylide would instead have a hydrogen and a methyl group rather than two methyl groups. So which option is better? Right, at first, it's hard to tell, and both of these would work, but one's better. Option 2 is the better one. Because remember, when I'm forming my ylide, it's an SN2 mechanism. So in option 1, my iodide would be secondary. Right? If I were to draw this sideways, I'll draw it sideways so it's more similar to what we have here. My hydrogen and my iodide. Right? The iodide gets substituted for the phosphorus group, and then I deprotonate to get my ylide, which is what I have right there. In option 2, this time, this is my alkyl halide. Then I react this and now get my phosphorus group, and I deprotonate and that's what I have right there in option 2. A primary iodide reacts better in an SN2 than a secondary does. So that's the reason I choose option 2, because I'm using a primary iodide for my SN2 reaction. So it's subtle, but there is a better option. So that's something to keep in mind when you're determining what reagents to use when you're given your product. One other thing I'd really recommend that I did here, right, is numbering the carbons. This would be carbon 3, 4, and 5. This would be carbon 2, and that would be carbon 1. So always number the carbons of your reagents to also make sure that you're using the correct reagents to form that alkene you're looking for.